Thank you very much indeed. So I've just been talking to a few people in the room here, and very interesting, a whole mix of backgrounds and interests, and yeah, questions being sparked a bit about, you know, how do I build a resilient system? How do I assess my requirements? Is the situation globally, you know, the geopolitical situation, does that make a difference or not? And the answer is yes. I mean, they're all very valid questions. And I did warn you that positioning, navigation, and timing is a very, very addictive topic. So let me try and carry on with a bit more. And I mentioned in the introduction, we're going, between Andy, Guy, and myself, we're going to try and give you like a practical way of rationalizing some of what you've just heard from Guy. What do I do about it? Well, if after this course we empower you with a bit of a toolkit to at least think through how to deal with and how to, you know, put some measure on the different factors that are at play out there, different vulnerabilities, different impacts, different effects, different realities, some of it just being physics. If we give you a bit of a toolkit to just think that through, maybe ask questions of your supplier, maybe ask questions of yourself and be able to sort of think of the option. Thumbs up, we've succeeded. And at the highest possible level, this is the approach we're going to sort of cover in the next, well, the rest of this session, actually, the rest of the day. So step A, requirements. So satellite navigation and navigation more generally and timing within that are used for everything. I mean, that's not much of an exaggeration. Maybe not my cup of tea down here, but anything vaguely technical does normally pick up some sort of position or navigation or time. And that means that the requirements are just so different between different applications. So having a view of requirements is a really key first step. And in this talk, I am going to talk about the different dimensions of requirements definition. You could do it in a huge way, or you could do it in a light way, but having some written, rationalized view of requirements is step number one. Having got that, put those requirements into the context of it says threats here, could say risk evaluation. Put the system into the environment that it's going to be operating in nominal conditions and extreme conditions and error conditions and so on. So test it out, do a risk assessment. I'm also going to cover that in this talk. And then beyond this talk is the purple on the right, which is, well, what can I do about it? So that's really to set the scene for this short talk here. So first of all, I'm going to talk about requirements, and then I'm going to come on to risk assessment. And Guy and Andy will pick up on these themes later on as well. So this is the most basic way of looking at and thinking of requirements in a navigation system. It's called RNP, Required Navigation Performance. In fact, most people, when you say how accurate, you know, I gave the game away. Most people, when you say, what requirement do you have for your navigation system? They say it's got to be 5 meters or better. They always define it in terms of accuracy. But even in this first cut view of requirements, accuracy is only one dimension. We all know what that means. In the position you've been reported, that's the accuracy, the difference between those two. The other three in this view are integrity, availability, and continuity. So integrity is whether or not you get a warning or some sort of flag of a problem or a potential problem. Just think about the applications you've used. You know, do you get an integrity flag? Well, one that we've all seen is the blue dot on mobile phones. And sometimes the blue dot's very tight, and sometimes it's got a sort of light blue around it. So that is an example of an integrity flag. Availability is the percentage of time the system needs to be available. So you've probably heard, 95% or 2 nines, 3 nines, 4 nines, etc. 99.99% of the time. And continuity is where you need a continuous reporting of a position. An app in a mobile phone actually is quite a good example of that. And you'll see in the rest of these talks how mobile phones are actually optimized to give you a position. Even if it's inaccurate, they'll give you a position so that when the app pings the operating system for a position, at least you'll get an answer. So that's the sort of very start of requirements. I would argue you should always define these for any positioning navigation system. What about, here's a question for the audience. What about if you've got a standalone GPS receiver, single frequency receiver that I mentioned this morning, up to 5 meters of error in a normal good conditions. Which of these is it going to put a tick on, and which of these is it not going to put a tick on? Well, accuracy is not bad, right? 5 meters or better anywhere in the world is pretty good. However, generally speaking, with a standalone GPS receiver, you're not going to get very good integrity flags, and it's not going to work all the time. Guy mentioned some of the reasons. So continuity and availability might not be perfect. Certainly not good enough if you've got a safety critical application. And it's very, very rare today to use just satellite navigation in any system. It's very unusual. This is just a taster of what's to come. It's much more usual to combine different systems together. And this is the classical marriage of 2 navigation approaches where you use GPS, which has got the characteristics I talked about on the previous chart, coupled with an inertial system, which actually is very difficult to jam or spoof or upset, but accuracy just gets worse over time. If you combine those 2 together, you get a better performance than either one in isolation. So I don't want to go into too much detail on that, but just gives you a concept that by bringing different technologies that are complementary together, you can yield a better result. But obviously what you need depends on your requirements. So let's carry on with requirements. So there's your so-called ACAI, the availability, continuity, accuracy, and integrity. And I've drawn it like that on purpose to visually represent that is just one corner of requirements definition. In fact, it's even one fraction of user requirements. So there are many different ways to define requirements. I mean, there are master's courses on defining requirements for systems. And system engineering itself is a whole nother discipline. So necessarily, this is just like a first principles type view that I'm going through. But I would always encourage at least to think of requirements definition for a system in terms of user, the needs of the user, the overall system aspects, and then the requirements of perhaps different elements that make up the overall system. What on earth do I mean by that? So just a flavor for that, I'll just flash through these. So the user would be worried perhaps about accuracy, but they might want to know about update rate. When if you're driving your car, for example, you would want a fairly regular update to your position on the map and the instructions that you're hearing. It's no good just getting an update every 10 seconds. It might need to be every second. Or maybe that's not enough. Maybe it needs to be twice a second. Otherwise you get the effect where you've left the roundabout and then you get the instruction to leave. We've all seen that, right? So that's an example of an update rate definition, requirement definition, I would say. It's a problem for the user, and so on. What interface are you going to use? How big's the screen? Budget as well is absolutely critical. I'm sure many of you have been involved in design and development, and guess what? It's always a compromise. Even if you're in the military, there's always a budget. You've always got to do it to a timeline. You've always got to make those trade-offs. The budget versus cost versus quality versus testing. It's always a trade-off. So that's some user requirement examples. System-wise, again, some of them are pretty simple actually. How big is it going to be? Where does it need to fit? What connections does it need? Guy said it's very unusual that a receiver is standalone, a receiver is part of a connected system. What power does it take? You know, I know it's basic stuff, but all of these questions can impact the system performance. If you've got a resilient power source or not, what happens if it switches to battery power, etc., etc., etc. So just going through these different levels can help. Also at the bottom, a small footnote on this chart, but a massive question for safety-related applications. I was just speaking to somebody in the room about rail. Yeah, I mean, certification, approval, testing in nominal conditions, testing in error conditions, testing in extreme conditions. How big is your test plan? All these questions come from, the answers to these questions come from a crisp and clear requirements definition. And then the third area is the different elements. Well, if you're going to have a satellite navigation system, or indeed, you know, Wi-Fi and cellular, you're going to need some sort of antenna. You're going to need a way to convert the radio frequency signal into a usable digital signal. That's the RF front end. You're going to need a clock. I mentioned the fourth thing to resolve is time. So your receiver clock is not very accurate, and it has to kind of sync up with the clock on the satellite. But what clock do you choose? How much do you spend on it? Who do you buy it from? Have you got all these questions? What algorithms are you going to use? What operating system? Is it Android or etc.? So I would advocate, in summary, trying to write at least a few pages, even for the most basic systems, and structuring them in some way. This is just one example of a way you can structure requirements definition. And then when you move on, the next phase, which is risk assessment, threat evaluation, you can start to evaluate your risks to the different vulnerabilities and physical effects. You can start to evaluate those in a structured way. If you haven't got the requirements, you're kind of just guessing a bit, shooting in the dark a bit. So that's a quick attempt at requirements definition. Then apply those requirements to the situation, the environment. And you're going to get fed up with me saying this, but risk evaluation and risk management approaches is a massive topic. I mean, we work with Warwick Manufacturing Group as one example, who have whole teams working on different approaches and different methodologies for assessing risks. I'm not going to go into that level of detail, but I'm going to present an approach which to me is logical and gets you kind of a good percentage of the way there. I wouldn't say it's quite the 80-20 rule, but this basic approach I'm about to will get you quite a way there in a structured way. So risks, you've probably seen them plotted quite often. How likely is it you're going to get experience this risk? And if you do experience the risk, what is the impact? What's the severity? That's a classical way of plotting risk, likelihood against severity. If you sort of take that to just a tiny step further, you might say risk is a product of the threat, the vulnerability, and the consequence. Where the threat is the probability of an adverse event, the vulnerability is the probability that that event would do you some damage, would impact your system performance, and consequence is the impact of that damage. So one of the first things to figure out then is, what is the family of threats and risks that you may be subjecting your system to? And in this list, I mean, make up your own list if you have a go at this. But in this list, the sort of starter for 6, these are characterized as, on the left here, natural or accidental. So things like space weather and inadvertent system errors, which certainly can happen. Unintentional interference, like that great example Guy gave of this Chinese farmer trying to protect his pigs from swine flu and taking out an airport. These are unintentional, accidental. And then on the right, a whole range of possibilities on that hierarchy that Guy showed, you know, right from nation state actors through to criminal activity, through to intentional hacking and so on. So there are some examples that your system might need to operate within, or at least you might need to understand your system performance within this environment. And then this model, this is the first of 2 or 3 charts on this model. You will get copies of these slides, so no need to quickly do it. I just want to get across the gist to you. The idea here is to apply some ranking to each of the factors. So vulnerability from not very much to a great deal. The same for consequence, and the same for probability of occurrence. And it could be just a 3-point scale, high, medium, low. And I would say don't angst over these too much. So when I started out with risk assessments, you know, earlier on in my career, I don't know. How should I know? I've no idea. I don't know what to, I'll hire a consultant, with all due respect to the consultants. I'll hire a consultant. And they say, well, is it high or medium or low, John? And I go, well, probably medium. They won't put that down. And, you know, high, medium and low is much better than trying to be too precise. If the resolution of the information you've got is only good enough to do high, medium and low, just put high, medium and low down. And when you flow it through a model like this, you'll still get a reasonably meaningful output. So I would just say have a go. Because whenever you have a working group sitting down looking at these factors, it's difficult. Don't get too detailed. Just look at the overall shape of your risk. That's the point of this model. Yeah, this is not a model for assessing aircraft safety for certification testing. This is a bit more than a wet finger in the air type model. Same with malicious acts. So what is the severity of the intent and the capability of the actor? So multiplying these two together gives you the threat of a malicious act. So when you might have somebody who's got an incredible bit of kit but hasn't got a clue how to use it. I won't mention any examples, but we could possibly think of some. And vice versa. So somebody who's got an incredible bit of kit but hasn't got a clue how to use it isn't much of a threat, quite frankly. So just trying to assess that. And then you can, I don't expect you to internalize all of this, but actually stand back from this and look at it through your, slitted eyes, because the idea is to put the factors in these first 4 lines and then multiply them together on the right-hand side. And the idea is to just give you, where are my biggest issues? And on this example, the answer to that question is for natural and accidental. The highest score is unintentional RF interference. And for malicious, the highest 3 scores are for criminal and privacy-related activity, terrorist jamming, and military-style jamming. So, this is just a particular example. So if that's the way that your answer comes out, then you can start thinking about the mitigations. What are you going to do about it? Focused on these highest ranking areas. Don't ignore the rest, but it gives you a bit of a structure to prioritize your thinking. And having done that, you can start thinking about the mitigation. So we're going to go on to this in the next few talks. What can you do about it? So here are the risk scores from the previous chart. And then I know you can't read these different column headings, but that's okay. These are different examples of mitigations you can take. And then you can start to look at how effective they may be in addressing the risk that you've identified. And as a spoiler alert, many of the mitigations can be fairly simple. Maybe, as an example, just to throw out there, you might want to use a better antenna. That makes a huge difference. Maybe you use an anti-jam antenna. Maybe you add inertial to your GPS system. Maybe, as the question before the break, you might want to combine Wi-Fi positioning with cellular positioning with GPS, and all of a sudden you've got a much more resilient system, albeit probably less accurate. So just by following this framework, it can really allow you to rationalize your situation. Let me just get back to that. Yeah, it can really help you rationalize your risk, your exposure to risks, and begin to give you a framework to prioritize your mitigation. And I do need to give some credit to the Resilient Navigation and Timing Foundation in the US. I think they're credited on the charts for really the origins of this model and encouraging everybody to use it. So this is the opposite of copyrighted. It's open source. Please, if it helps you. If anybody wants a spreadsheet version of this, I do have it and can share that offline as well. Okay, so I'll now stop there and invite Guy to introduce the concept of a system of systems to improving resilience.